Most of us walk around with a comforting kindergarten image of Earth's place in space, a tiny blue marble tracing a tidy circle around the sun, like a student who has been told to stay inside the chalk line. It is a simple picture, safe, predictable, and about as accurate as saying a tornado is just windy. The truth is far wilder, far stranger, and honestly way more fun, because Earth is not calmly orbiting anything. Earth is holding onto the sun for dear life, while the entire solar system blasts through the galaxy like a cosmic theme park ride that forgot to install brakes. If planets could scream, we would never have a quiet moment again. This idea that our planet is soaring through the Milky Way on a path that looks more like a spiraling roller coaster than a polite ellipse is the kind of thing that should be printed on every classroom wall right next to "Gravity exists." But it rarely is, mostly because it is hard to draw and even harder to fit on a test. Yet once you hear it, you cannot unhear it. You suddenly realize that Earth is not a passive bystander in the cosmos. It is a passenger on a star that refuses to sit still. The sun is like that friend who says, "We are just going out for a quiet walk," but then somehow you end up paragliding off a cliff while holding snacks you did not agree to carry. So here is the twist. Earth's motion around the sun is real, yes, but that loop is just the tiniest part of a much grander path. Imagine you are riding a carousel horse. Now imagine the entire carousel itself is mounted on a sports car, doing laps around a racetrack. Then imagine that racetrack is actually built onto the back of a flying whale migrating across an ocean the size of a galaxy. That is closer to what Earth's path actually looks like. Our orbit is only a decorative flourish on top of the enormous motion of the sun as it races through the Milky Way. Earth is not circling in place. It is carving a vast spiraling trail through interstellar space, a path that looks like the universe tried to draw a spring but sneezed halfway through. The funny thing is that humans have spent centuries studying the heavens, charting orbits, naming constellations, predicting eclipses, and building entire calendars around where Earth will be tomorrow, next year, or 10,000 years from now. Yet none of these timekeeping traditions mention the fact that we are speeding through space at a pace that would make even the bravest amusement park engineer say, "Maybe that is too much." We talk about sunrise and sunset as if the sun gently glides across a still sky. In reality, both we and the sun are moving so fast that if space had speed limits, the universe would confiscate our license. But speed alone is not the surprising part. What shocks most people is the shape of the path itself. It is not a circle. It is not an oval. It is not even a tidy spiral. It is a swirling, sweeping, three-dimensional arc that looks like the signature of a caffeinated physicist. Earth's path is motion layered on top of motion, a loop nested inside a drift, nested inside a galactic journey so massive that even metaphors start sweating. And the wildest part is that this is the calm version. This is the everything is currently stable mode. If Earth ever had a slogan, it would be, "Moving through the galaxy since forever, still not sure where the brakes are." What makes this concept so delightful is how it flips our perspective. We tend to imagine the universe as something we look at, something out there, separate from our daily lives. But the moment you picture Earth as a moving spacecraft, one that never stops, never slows, and never takes the same route twice, you realize you are not living on a quiet, static planet. You are living on a cosmic traveler. Every second of your life, you have been streaking through the galaxy without a window seat, without a seat belt, and without the faintest idea of the ride you were on. The universe did not ask for your consent. It simply said, "Buckle up, you are coming with us," and off you went. And that is the real hook, the moment the story opens up. Because once you understand that Earth's motion is nothing like the gentle orbit you learned in childhood, you start to wonder what this path looks like, where it leads, what forces sculpt it, and how this wild cosmic journey has shaped everything from our atmosphere to our distant future. Earth's galactic path is not a footnote in astronomy. It is the secret adventure we have been on the entire time, a journey so vast we only notice it when someone points at the sky and says, "By the way, you are not where you think you are." And that is where our story begins, with the realization that Earth is not circling the sun. Earth is surfing the galaxy. The cosmic roller coaster is already in motion, and we are just now opening our eyes to the view. If the sun ever filled out a cosmic resume, the first line would say something like, "Local star, self-powered fusion reactor, currently traveling at a speed that would make most spacecraft explode from sheer embarrassment." Because the sun is not lounging lazily at the center of our solar system like a monarch surrounded by obedient planets. It is sprinting, always sprinting, around the center of the Milky Way with the urgency of someone who just remembered they left the house unlocked. And because Earth is tethered to the sun by gravity, we get pulled along automatically, no ticket required, no refunds available. To grasp just how fast this star is moving, picture the fastest jet you can imagine. Then forget it. Because the sun leaves that thing in the dust without even noticing there was dust. Our star speeds around the galaxy fast enough that if space had windshields, the sun would need a new one every hour. And because Earth is clinging to this star like a roller coaster rider clutching the safety bar, our planet is not simply orbiting. It is being carried through space as part of a larger, grander motion that no classroom diagram ever warned you about. This motion is the reason your familiar picture of Earth's orbit, an elegant oval drawn around the sun, needs a dramatic makeover. That oval is technically correct, but only if you freeze the universe in place. In reality, the sun never stops moving forward, which means Earth's path is constantly being pulled ahead with it. So instead of drawing a flat loop, imagine taking that loop and stretching it into a spiraling shape that winds endlessly forward. The result is a helix, a kind of cosmic spring, except this spring is made of planetary motion instead of metal coils. If you could paint Earth's actual path in space, it would look like a glowing blue ribbon twirling behind a star on the run. And what gives the sun this permanent case of cosmic wanderlust? Gravity. But not the gentle, polite gravity we feel on Earth that keeps our feet on the ground. This is the heavyweight champion version of gravity that dominates the entire galaxy. The Milky Way is filled with hundreds of billions of stars, swirling gas, dark matter, and more gravitational interactions than a ballroom full of dancers trying not to step on each other. At the center lies a gravitational well so deep it bends the very fabric of space. The sun has no choice but to orbit the center, caught in the galaxy's massive gravitational choreography. The star's journey traces a wide, curving path tens of thousands of light years long, and it completes one lap only after wandering through space for hundreds of millions of years. If the sun ever tried to stop, the galaxy would simply tug it back into line like a cosmic crossing guard saying, "Nice try, but no." And because Earth is gravitationally bound to this star, our planet must follow every move it makes, like a younger sibling forced to tag along on an older sibling's road trip. This constant forward motion reshapes Earth's orbit in a way that is both elegant and slightly chaotic. A simple loop around the sun becomes a twisted, forward-moving spiral. Each year, Earth completes a circuit, but that circuit is never in the same place twice. It is always shifted, always carried further along the sun's path. You can imagine the sun as a teacher walking down a hallway, while Earth repeatedly circles them, tracing loops that trail behind in a long, curling ribbon. That ribbon stretches for billions of kilometers, a shimmering sign of our motion through the galaxy. And the shape is not just pretty, it has consequences. Because Earth's orbit is part of this forward surge, our planet is constantly sweeping through new regions of interstellar space. We are always in motion relative to everything around us, not floating in a static backdrop, but moving through a cosmic environment that shifts over time. The solar wind, the magnetic field, the flow of interstellar particles, all of it changes subtly as we travel. It is like driving through a landscape where the scenery never stops changing, even if the road feels smooth beneath your feet. The sun's speed also affects the scale of our journey. While we happily measure years by how long Earth takes to orbit the sun itself could not care less. It is busy completing a far larger circuit of its own, a journey so immense that the entire history of humanity accounts for only a tiny fraction of it. Every moment we live is one frame in a cosmic animation that began long before our species existed and will continue long after we are gone. We are passengers on a star that never stops moving, a star that refuses to stay put for even a moment. And so the truth becomes clear. Earth does not orbit the sun the way a coin circles the center of a merry-go-round. We orbit a moving target, one that drags space, planets, magnetic fields, and everything else along with it. Our orbit is a side effect of a much grander motion, a spiraling helical path shaped by a star racing through the galaxy. The next time you picture Earth's orbit, do not imagine a quiet cosmic loop. Imagine a spinning blue planet chasing a runaway star through the Milky Way, leaving behind a swirling trail of motion that stretches across the galaxy like a signature written in light. If someone ever handed you a postcard of the Milky Way, you might assume it was photoshopped. It looks too perfect, like some cosmic pinwheel, equal parts elegant and intimidating, twirling endlessly in the quiet blackness of space. But that postcard image is more than a pretty spiral. It is the gravitational architecture that dictates how every star, nebula, rogue comet, and confused dust grain inside the galaxy must move. And sitting inside this astronomical spiral is our sun, tucked away in a spot that is neither too central nor too remote, a kind of cosmic suburb known as the Orion Arm. It is the galactic equivalent of living a few exits away from downtown, close enough to feel the traffic, but far enough to stay out of the drama. The Milky Way itself is shaped like a vast, flattened disk with sweeping spiral arms that curl outward from a central bar. If you could hold the galaxy in your hands, ignoring that it is 100,000 light-years wide and would probably evaporate your hands instantly, you would see a bright bulge in the middle, surrounded by long, graceful arms looping around it. These arms are not solid structures, but more like pressure waves, regions where gas and dust are packed more tightly, and where new stars tend to ignite like cosmic streetlights. The whole galaxy rotates with the smoothness of a spinning vinyl record, except this record is full of star clusters, supernova remnants, and the kind of gravitational drama that would make any astrophysicist reach for popcorn. Now imagine this disk from above, turning slowly, each arm sweeping through space like a colossal celestial paintbrush. Our sun does not sit in the middle of one of those prominent arms. Instead, it resides in a smaller, quieter region called the Orion Arm, or sometimes the Orion Spur, which sounds like either a modest galactic feature or a Western-themed space tavern. This arm is a minor branch tucked between two much larger and showier arms, the Perseus Arm and the Sagittarius Arm. Those big arms are where the galaxy likes to show off. Bright star-forming regions, massive clouds of gas, and clusters glowing like neon signs announcing, "New stars! Get your new stars here!" By contrast, the Orion Arm is like the peaceful neighborhood where stars go to enjoy a modest but stable existence. That does not mean it is boring. It simply means that our sun grew up in a region where the gravitational forces, stellar densities, and cosmic hazards are all reasonably balanced. Living here is a bit like running on the inside lane of a racetrack. The journey is smoother, the curves are gentle, and you do not have to constantly dodge the kind of high-energy chaos that would make planetary evolution significantly more stressful. This position also shapes the trajectory of our solar system as it flows along with the galaxy's rotation. Since the Orion Arm is relatively narrow and situated between heavier structures, the gravitational pull in this region is more symmetric than it would be inside one of the major arms. That symmetry affects how the sun moves, keeping its path stable enough for planets to form and remain comfortably in orbit rather than becoming stellar frisbees. The sun drifts within this arm, much like a boat carried gently along a broad, slow-moving river, steady, predictable, and guided by the overall flow rather than any one disruptive force. The shape of the galaxy itself plays a crucial role in this motion. The Milky Way's spiral arms are not static decorations. They are dynamic regions shaped by density waves, ripples of higher density that sweep through the disk, gathering material into star-forming regions as they pass. It is not that stars stay locked in their arm like traffic stuck in a lane. Instead, stars drift in and out of these arms over millions of years, much like running alongside a parade, long enough to feel like you are part of it, even though you were never officially invited. But because we are in a minor arm rather than a major one, the sun's journey is less chaotic. There are fewer massive gravitational anomalies tugging on our orbit, fewer giant molecular clouds threatening to disrupt our path, and far fewer high-energy stellar neighborhoods that might fry everything we love with cosmic radiation. The Orion Arm is the perfect example of galactic middle ground, not too bright, not too dense, not too wild. It is basically the Goldilocks zone of galactic real estate. This placement also determines the angle and characteristics of our solar system's trajectory. As the galaxy rotates, the arm itself gently curves inward toward the galactic center, guiding the sun along a smooth arc that blends forward motion with rotational drift. If the galaxy is the racetrack, then our orbit is the inner ring, shorter, faster, and more stable than the sprawling, chaotic paths further out. The sun's motion follows this spiral lane with a kind of understated grace, not because it chooses to, but because the gravitational architecture of the Milky Way insists on it. All of this means that Earth's cosmic journey is shaped not only by our orbit around the sun, and not only by the sun's sprint around the galaxy, but by the grand design of the Milky Way itself. Our location in the Orion Arm places us in a privileged position, sheltered enough for life to flourish, stable enough for planets to persist, and dynamic enough to keep astronomers endlessly fascinated. The Milky Way is the racetrack, the Orion Arm is our lane, and the sun is our endurance runner tracing that spiral path with billions of years left to go. If space had weather reports, the very first thing they would mention about our neighborhood is that we live inside a bubble. Not the fragile soap kind you blow on a summer afternoon, but a colossally large cavity carved out of the galaxy by explosions so powerful they could make a star rethink its life choices. This enormous region, known as the local bubble, is the cosmic equivalent of an empty auditorium, vast, quiet, and mysteriously hollow compared to the crowded stellar suburbs around it. And right now, the entire solar system is cruising through this enormous void, like someone who accidentally wandered into the backstage area of the Milky Way and decided not to ask questions. The local bubble is an odd place because it does not behave like most regions of interstellar space. Usually, the galaxy is full of gas, dust, and drifting particles that give space a kind of thin, interstellar soup texture. But here, inside this bubble, the density of matter is drastically lower. It is as though someone scooped out the region and forgot to put the ingredients back in. For reasons we now understand, the bubble is not simply empty. It is the charred aftermath of at least a dozen ancient supernova explosions, each one blasting out enormous shockwaves that cleared away the surrounding gas like a cosmic leaf blower set to maximum power. These explosions happened millions of years before the sun strolled into town, lighting up the galaxy before fading into silence. Each supernova sent out expanding shells of charged particles and high-energy radiation, carving out overlapping cavities that fused into the enormous structure we drift through today. If you could watch the whole thing in a time-lapse animation, it would look like a series of huge ripples in space, colliding and merging until they formed one gigantic bubble, an interstellar bruise left behind by stars that lived fast and died spectacularly. The result is a cavity roughly shaped like a lopsided oval, extending hundreds of light years across. It has boundaries, thin glowing walls of gas and dust, like the edges of a cosmic crater. Those walls are not solid, but they are denser than the interior, gently glowing from the heat of compressed particles. Think of them as the faint afterglow of explosions long extinguished, faint cosmic fingerprints of stars that decided to go out in maximum volume fashion. Now, the sun did not form inside this bubble. Our star is merely passing through it, like a commuter cutting across an empty stretch of highway carved long ago by someone else's construction crew. The sun entered this region sometime in the last few million years, and it will eventually leave through the opposite side, continuing its journey through the galaxy. But while it is here, the bubble influences everything from the shape of the solar system's protective magnetic envelope to the way interstellar particles drift around us. Inside the local bubble, the solar wind has more room to stretch its legs. Normally, the solar wind, which is that steady stream of charged particles flowing outward from the sun, must push against the thicker gas of interstellar space, like someone trying to blow up a balloon that fights back. But inside this cavity, the interstellar gas is so thin that the solar wind can inflate our heliosphere farther, creating a more spacious protective bubble around the solar system. It is not exactly luxurious, but in cosmic terms, it is the difference between living in a cramped studio apartment and suddenly discovering you have a backyard. This low-density environment also affects how cosmic rays, those high-energy particles zooming through the galaxy, reach us. The boundaries of the local bubble act like a partial shield, slowing some of them, redirecting others, and absorbing a few. It is not a flawless defense system, more like a slightly leaky fence, but it does shape the intensity and patterns of the radiation that reaches our solar system. Without even noticing, we live in a cosmic region that moderates the energetic particles pelting our planet, a kind of quiet guardian formed by explosions long past. What makes the local bubble even more fascinating is that it is not static. As the sun moves, we travel through different parts of this cavity, each region with its own density quirks and radiation patterns. The bubble is also evolving, expanding slightly at its edges as heat and pressure slowly push outward. Imagine a very slow motion balloon inflating over hundreds of thousands of years with no party guests in sight. Scientists still debate exactly how uniform its interior is, how sharply its walls are defined, and how many ancient explosions contributed to its shape. But what is clear is that our cosmic neighborhood is not a quiet, neutral backdrop. It is the relic of violent origins that continue to influence us. Even more intriguing is that our sun is now approaching a boundary region where the local bubble meets a neighboring interstellar cloud. When we eventually cross that frontier far in the future, the heliosphere will shrink again, the solar wind will face new resistance, and the cosmic weather will change subtly but noticeably. We will be travelers passing from one vast and ancient space into another, like explorers sailing out of a calm, cleared-out bay into a deeper, more textured ocean. The local bubble may be a quiet region now, but its history is written in supernova shockwaves, and its influence shapes the environment through which our solar system moves. It is a silent stage beneath our cosmic journey, unseen yet essential, an ancient void carved by dying stars that unknowingly sculpted the path we travel today. If you thought the sun's motion around the galaxy was already complicated enough, speeding forward, dragging planets, tracing spirals, you may want to tighten your seatbelt because there is another layer to the story. The sun does not simply move in a flat disk like a coin sliding across a table. It performs a slow, graceful bobbing motion up and down through the galactic plane, as if the entire solar system were riding a cosmic merry-go-round that occasionally forgets it is supposed to stay level. This movement is called vertical oscillation, a term that sounds like it belongs in a physics textbook, but really just describes the sun's habit of drifting above and below the main disk of the Milky Way, in a cycle so leisurely it makes continents look impatient. Imagine the galaxy as a giant cosmic pancake, thick with stars, gas, and dust, all flattened into a disk. Now picture the sun not staying flat within that pancake, but gently bouncing through it, moving upward for millions of years before slowly drifting back down. It is not a dramatic jump, no acrobatics, no stellar parkour, just a soft rise and fall, like a buoy floating on a very slow-motion cosmic tide. You could live your entire life, and your grandparents' lives, and every life recorded in human history, and the sun would barely be finishing a tiny fraction of one of these vertical cycles. It is the long-term astrophysical equivalent of a relaxed shrug. This vertical motion happens because the Milky Way's disk has mass, and mass means gravity. Most of that mass sits near the midplane, the central layer of the galaxy where stars are most densely packed. When the sun drifts upward, gravity gently tugs it back toward the midplane. When it drifts below, the same gravitational pull lifts it back up. It is a cosmic balancing act. The sun overshoots the center slightly, then gets pulled back the other way, repeating the pattern in a cycle spanning tens of millions of years. The whole solar system is like a bird riding rising air currents, gliding gently above and below the galactic sheet, without ever settling into a perfectly flat orbit. What makes this oscillation more than a fun visual is how it transforms the sun's path from a simple spiral into a three-dimensional helix with a subtle wobble. Without this vertical motion, the the solar system's journey would look like a neat, stretched out corkscrew. But the up and down drift adds texture, like someone nudged the corkscrew while it was being drawn. It gives our path a wavering quality, a gentle cosmic sway that adds personality to an already elaborate galactic journey. If our motion through the Milky Way were choreography, this would be the flourish at the end of each step. A slight upward rise, a downward dip, then forward motion resuming as though nothing unusual happened. The vertical oscillation is also a reminder that the galaxy is not a smooth, uniform structure. Its gravitational pull changes depending on where the mass is concentrated. The Sun feels these variations like a surfer reading the shape of the water beneath them, subtle, long-term influences that shift the flow of the journey without altering its destination. Each bobbing cycle is shaped by the distribution of stars, dark matter, and interstellar gas around us, all tugging gently at the solar system as it moves. Space is not empty. It is a gravitational landscape sculpting our path in ways we rarely imagine. This up and down drift also means that the solar system spends different stretches of time in slightly different regions of the galactic disk. When the Sun rises above the mid-plane, we move into a thinner, quieter region with fewer stars around us. When we dip below, we enter a denser neighborhood where the galaxy feels a little more crowded. These changes are incredibly subtle on human timescales, but over millions of years, they alter the environment through which our system travels. It is similar to sailing across an ocean where the water depth changes gradually. Sometimes you glide over deeper waters, sometimes over shallower ones, and the movement feels different each time. The oscillation itself is not perfectly regular. The galaxy is full of gravitational bumps and uneven mass distributions that occasionally speed up or slow down the Sun's vertical drift. This is not a tidy pendulum motion, but a natural, slightly messy rhythm shaped by everything around us. The Sun is not counting cycles. It is simply responding to the gravitational architecture of the Milky Way, drifting through it like a lantern suspended on invisible currents. One of the most surprising things about this vertical motion is how quietly it happens. Nothing on Earth alerts us to the fact that we are rising or falling relative to the galactic plane. Birds continue migrating, oceans continue sloshing, and everyone goes about their lives unaware that the entire solar system is moving in 3 dimensions with a subtle but persistent wobble. The effect is too gentle to influence daily life, too slow to measure without sensitive instruments, and too enormous to visualize without stretching the imagination across millions of years. Yet this gentle bobbing adds another layer to the story of our cosmic journey, reminding us that motion in the universe is never as simple as it seems. Earth is not orbiting in a flat sheet of stars. It is part of a system that drifts up and down in a rhythm as old as the galaxy itself. Our path is not just a forward spiral. It is a spiral that tilts, dips, and rises in a graceful galactic dance that continues endlessly, shaping the story of our travel through space. The Sun's vertical oscillation offers a quiet truth. Even when you think you understand the motion of the cosmos, There is always another layer, another direction, another influence, another subtle wave shaping the journey. It is the universe's way of saying, 3 dimensions are never enough. If the sun imagined its journey through the galaxy as a smooth, elegant path, an unbroken spiral carved with mathematical precision, reality would politely cough and say, "About that." Because the Milky Way is not an empty racetrack with clean lanes. It is crowded. Stars wander, clusters drift. Enormous clouds of gas lumber through space like celestial whales, and all of these things tug, ever so slightly, on the sun. The result? Our solar system's path is not the cosmic equivalent of a calligrapher's perfect curve. It is more like the doodle you make while talking on the phone, mostly smooth, but with tiny wobbles where gravity interrupts to say hello. Every star in the galaxy exerts gravitational influence on every other star. Most of the time, those forces average out so well that the sun's main motion remains dominated by the grand gravitational pull of the Milky Way. But occasionally, and inevitably, the sun wanders close enough to another star for that star's gravity to give it a gentle nudge. Not a shove, nothing dramatic that sends planets flying like startled birds, but just enough to alter the sun's trajectory by a whisper. Over millions of years, those whispers add up. The sun's journey becomes subtly bent, curved, warped in places where unseen neighbors passed close enough to tug at our course. Even today, the sun has companions drifting near us, not close enough to be considered dangerous, but close enough to leave faint fingerprints on our motion. Stars like Alpha Centauri, Barnard's star, and a whole crowd of dim red dwarfs wander within a few light years of our neighborhood. They drift in and out like quiet pedestrians walking past your house. You might not notice them individually, but collectively they participate in a kind of cosmic tug-of-war. The forces involved are tiny but constant, little nudges that keep our spiral from being perfectly symmetrical. Then there are the star clusters. These are gravitationally bound families of stars, sometimes hundreds or thousands of them, moving together through the galaxy like migrating cosmic towns. Their combined gravity can influence passing stars in ways that individual neighbors never could. When the sun moves near one of these clusters, it feels a stronger collective pull, the way a boat might be nudged by the wake of a large ship passing by. The sun may not dramatically change direction, but its path bends ever so slightly, just enough to give our orbit a new tilt or curve. Over long timescales, these subtle interactions stitch tiny variations into our trajectory. Variations that do not disrupt the solar system, but do ensure our path is never exactly the same twice. But perhaps the most surprising sources of gravitational influence are molecular clouds. Vast, cold regions of space filled with gas and dust, thick enough to collapse into new stars. These clouds can span dozens of light years and weigh more than 1,000,000 suns. They are slow-moving, silent giants drifting through the spiral arms. And when the sun approaches one, even from afar, the cloud's gravitational pull can influence the sun's motion. It is like being on a bicycle and feeling the faint pull of a gentle slope in the landscape. You barely sense it, but it changes your direction nonetheless. A molecular cloud does not yank the sun around like a wild beast. The distances are far too large for that. Instead, the cloud exerts a steady, subtle pull that bends the sun's path like a garden hose curving around a rock. We glide past, our trajectory slightly reworked, our forward motion gently re-aimed. To the sun, this is not unusual. It has been drifting past such clouds for billions of years. But to us, it means that Earth's galactic path is full of tiny variations, little turns, sways, and arcs that reflect the invisible influences of massive structures that pass nearby. These slight bends do not affect the stability of our solar system. The planets continue orbiting the sun as usual, but the sun's long-term path through the galaxy becomes a tapestry woven with countless gravitational interactions. It is not a spiral drawn by a single steady hand. It is a spiral shaped by billions of years of encounters, each one adding a subtle deviation, each one making the line wobble just enough to give it a personality. You could imagine the sun trying to walk in a straight line while friendly but persistent neighbors tap it on the shoulder every few million years. It keeps moving forward, but its steps shift slightly, adjusted by the last tap. The galaxy is full of these taps, soft, gravitational nudges that ensure nothing in the Milky Way ever moves with perfect geometric precision. Gravity is democratic. Every object gets a vote, even if some votes are much louder than others. Because of these interactions, the sun's path resembles something beautifully organic. It has the elegance of a spiral, but with the imperfections of a hand-drawn sketch. The galaxy is not a place for perfectly engineered trajectories. It is a place of dynamic influence, where stars drift, clouds migrate, and gravitational fields overlap in intricate patterns. And the sun, carrying Earth along for the ride, responds to all of it. Our solar system's journey is therefore not a static curve carved into space. It is a living, evolving path shaped by every massive neighbor the sun encounters. The planets orbit smoothly. The sun moves steadily. But the galaxy whispers, nudges, and adjusts our course in ways that make our journey uniquely textured. And because of those subtle influences, Earth's passage through the Milky Way becomes less the idealized path drawn in textbooks and more a cosmic doodle, beautiful, intricate, and shaped by forces we never see but always feel. If the galaxy were a city, dark matter would be the mysterious city planner who never shows up in photographs, never signs their name on anything, and yet seems to have designed every road, bridge, and intersection. You cannot see this planner, you cannot shake their hand, and you definitely cannot ask for directions, but every movement within the city quietly obeys their influence. Dark matter is that invisible architect, unknowable to the eye, undetectable to our touch, but essential in shaping the path the sun follows as it sails through the Milky Way, with Earth tagging behind like a determined backpack. The strange thing about dark matter is that it does not behave like ordinary matter. It does not glow, burn, absorb energy, bounce off anything, or even interact with light. If you tried to grab a handful of it, your hand would pass through as easily as through a ghost, and it would remain completely unimpressed by your efforts. And yet, for reasons rooted in gravity, it controls the majority of the mass in the galaxy. That means dark matter is the heavyweight champion of the Milky Way, quietly dominating the gravitational landscape, while ordinary matter, stars, planets, gas, dust, plays the supporting cast. The Milky Way, as majestic as it appears in colorful renderings, is only the bright skin of a much larger structure. Dark matter surrounds and permeates the galaxy in a huge halo extending far beyond the glowing spiral arms. This halo is not a tidy sphere, but more like a diffuse, uneven cloud of invisible mass. It exerts gravitational influence in all directions, shaping how the galaxy rotates, how stars drift, and how the sun finds its long-term orbit around the galactic center. Without dark matter, the Milky Way would spin apart like a poorly fastened carnival ride. With it, the galaxy holds together in a gravitational embrace strong enough to choreograph the motion of billions of stars. Now, if dark matter were evenly distributed, its influence would be somewhat predictable, a steady, gentle pull felt in every direction. But the halo is not uniform. It has clumps, filaments, and shifting density regions left behind by ancient mergers, collisions, and the long history of galaxies cannibalizing their neighbors. As the sun moves through the galaxy, it travels through this dark matter landscape like a ship drifting through an invisible ocean. The currents are subtle, but they are everywhere, adding small but persistent gravitational nudges that shape the sun's path. These nudges are not abrupt or dramatic. Dark matter is not hurling rocks at us or pushing the sun around like an impatient cosmic bully. Instead, imagine drifting through a landscape where the hills and valleys are invisible but still affect the direction your boat takes. Over millions of years, the sun feels these gravitational contours, adjusting its orbit ever so slightly as it travels. No one deviation defines our path, but the collective influence of dark matter shapes the curve of the sun's long-term trajectory. This influence becomes especially important when considering the sun's speed around the galaxy. Stars move far faster than their visible mass suggests they should. If only the mass we can see, stars, gas, dust, were exerting gravity, the sun would spin off into intergalactic space like a child flung from a malfunctioning merry-go-round. But because dark matter supplies the missing gravitational mass, the galaxy rotates smoothly. The sun stays bound in its enormous circuit, not because of what we see, but because of the enormous invisible mass lurking in the dark matter halo. Dark matter also makes the galaxy's gravitational field more rounded and symmetrical than it would be if only visible matter were involved. Ordinary matter is clumpy. It collects in stars, clouds, clusters, and spiral arms, creating a patchy gravitational environment. But dark matter, being more evenly dispersed on large scales, smooths out many of those irregularities. It acts like a cosmic stabilizer, ensuring that stars follow long-term paths that remain coherent even as they drift through a galaxy filled with chaotic, visible structures. To the Sun, this stabilizing influence means that its galactic orbit does not wobble wildly with every passing star cluster or molecular cloud. Dark matter anchors the entire system in a gravitational field that is far larger and smoother than anything made of normal matter. It is the difference between riding a bicycle on a freshly paved road versus a cobblestone alley. The bumps from visible matter are still there, but dark matter provides the underlying shape that keeps the Sun's path consistent over billions of years. In this quiet but profound way, dark matter becomes the galaxy's traffic controller. It does not direct any one star individually, nor does it send out memos or carve signs into the sky. But its gravitational presence establishes the framework within which every star must move. It is the unspoken rulebook of galactic motion, the invisible architecture that determines which orbits are stable and which trajectories even exist. Without dark matter, the Milky Way's structure would collapse. The Sun's path would disintegrate, and Earth would drift into a cosmic wilderness with no roadmap and no guiding force. Instead, thanks to dark matter, our solar system follows a graceful, predictable arc through the galaxy, a path sculpted by something we cannot see, cannot touch, and yet depend on entirely. Dark matter does not ask for credit. It does not shine. It does not roar. It does not display itself with any flair. But silently, subtly, and profoundly, it shapes the cosmic playground in which our Sun moves. And in doing so, it shapes the journey of Earth as well, guiding us along a path written in gravity by an invisible hand. Most people imagine the Milky Way's spiral arms as if they were permanent, solid highways, grand, luminous trails of stars that the Sun obediently follows like a car merging into traffic. But the truth is far stranger. Spiral arms are not physical structures you could point to as fixed locations. They are more like cosmic traffic jams, regions where matter temporarily piles up due to the galaxy's internal dynamics. Stars drift in and out of them, passing through the bright arms the way a commuter might slip through a bustling downtown before returning to quieter suburbs. The Sun is one such drifter. It does not live permanently inside a major spiral arm. Instead, it wanders between arms over the course of millions of years, entering regions of increased stellar density and then gliding back out into calmer pockets of space. Each passage subtly changes the cosmic environment around Earth, affecting everything from the intensity of radiation that seeps into our atmosphere to the amount of interstellar material the solar wind must push aside. The galaxy's spiral arms may be beautiful, but they are also the architects of shifting cosmic weather that Earth has experienced throughout deep time. To understand why these arms are not fixed structures, imagine the Milky Way as a giant rotating disk. The disk spins, but the stars inside it do not move at the same speed. Instead, stars at different distances from the galactic center orbit at different rates. Spiral arms appear not because stars are arranged in fixed patterns, but because density waves, vast, slowly rotating gravitational disturbances, travel through the disk, compressing gas and dust as they go. These waves rotate more slowly than the stars, meaning stars like the Sun sweep into an arm, linger there for millions of years, and then drift back out again as they continue their orbit. In that sense, passing through a spiral arm is less like taking a road and more like wandering into a city undergoing a parade. You enter the crowded street, everything gets brighter and busier, and then eventually you emerge into quieter territory once more. The Sun has done this many times over its lifespan. Each time it enters a spiral arm, it encounters regions that are richer in star-forming gas and peppered with young, hot stars. These youthful stars radiate enormous amounts of high-energy ultraviolet light, bathing the region in intense radiation. Meanwhile, the density of material in these areas is higher, which means more cosmic dust, more charged particles, and more energetic events like stellar explosions. Earth does not notice this transition overnight. These changes unfold at a pace so slow that even continents cannot keep up. But over tens of millions of years, the cosmic environment shifts in subtle but meaningful ways. The radiation level rises slightly as we approach clusters of brilliant newborn stars. The solar wind must wrestle with thicker waves of interstellar particles, adjusting the size and shape of the heliosphere that shields our planet. Cosmic rays may become more abundant or more intense depending on the location and recent activity of nearby massive stars. One of the most striking effects occurs when passing near star-forming regions, which are fertile grounds for powerful events like supernova explosions. A supernova within a few dozen light-years of Earth would be an extraordinary spectacle, not the sort of fireworks show you want too close to your atmosphere. Although such events are rare, drifting through spiral arms statistically increases the chances of encountering massive stars nearing the end of their lives. Some researchers have speculated that bursts of high-energy radiation from these events may have influenced Earth's ancient climate patterns or left imprints in geological layers, though the details remain an open and fascinating question. The shifting environment also affects the interstellar material that interacts with Earth's atmosphere. Regions nearer spiral arms contain more dust clouds and gas streams. As the Sun plows through them, this material changes how cosmic rays penetrate the heliosphere and how charged particles accumulate around the solar system. On Earth, these influences might subtly affect cloud formation, atmospheric chemistry, or the long-term balance between warming and cooling cycles. Nothing catastrophic happens overnight, but the solar system does feel the difference, like a ship noticing a slight change in water currents as it enters a new stretch of ocean. Yet the most dramatic part of this story is that spiral arms do not move in lockstep with the Sun. They rotate at a different speed from the stars themselves. So while the Sun steadily orbits the galactic center, the arms slide past in slow motion, and the Sun catches up to them periodically. The timing of these crossings is measured not in years, but in epochs. Civilizations rise and fall far too quickly to notice. Entire species appear and vanish before the Sun even completes one transition. Today, our solar system resides between major spiral arms in a relatively peaceful region where stellar density is modest and the cosmic environment is calm. It is a quiet neighborhood, not empty, but certainly less intense than the bustling, luminous chaos of a main spiral arm. This tranquility has likely been helpful for life on Earth, reducing the frequency of disruptive cosmic events and allowing biological evolution to unfold in relative safety. But the peace will not last forever. The sun continues its long trek through the galaxy. One day, millions of years from now, it will again drift into denser territory, entering a fresh spiral arm with a new cast of stars, new cosmic weather, and a new backdrop of galactic activity. Earth will not merely orbit the sun, it will ride through these shifting environments like a traveler moving through different biomes, each with its own unique conditions. Our passage through the galaxy is not a straight shot. It is a journey through changing landscapes, sculpted by the Milky Way's grand dynamics. Spiral arms are not destinations. They are environments we drift through, shaping Earth's cosmic climate in ways both subtle and profound. Long before galaxies formed their grand spirals, and long before stars carved light into the darkness, the universe released a final sigh of heat, its last glow from an era when everything was squeezed together in a dense, fiery fog. That glow never disappeared. It simply stretched, cooled, and dimmed as the universe expanded. Today, it fills all of space as a faint bath of microwave radiation called the cosmic microwave background, or the quiet after-echo of the Big Bang. It is the oldest light in existence, a relic so ancient it has been traveling across the cosmos for more than 13 billion years, just waiting for someone or something to drift through it. And that something is us. When astronomers measure this ancient radiation, they expect it to look the same in every direction, like the perfectly even glow of an old fireplace that has burned down to its last embers. But it does not. It is slightly warmer in one direction and slightly cooler in the opposite one. That tiny imbalance is not caused by the universe being lopsided. It is caused by us moving, hurtling actually, through this ancient light at a speed that makes our motion around the galaxy feel like a warm-up jog. The solar system is not simply orbiting the sun, not simply spiraling through the Milky Way, but drifting through the cosmic background itself, creating a sort of Doppler effect in the universe's oldest whisper. Imagine riding a bicycle through still air. If you pedal fast enough, the breeze feels stronger on your face and weaker behind you. The same thing happens with light. Because we are moving relative to the cosmic microwave background, the radiation in the direction we are heading looks ever so slightly compressed, warmer, bluer, while the radiation behind us is stretched, cooler, redder. This temperature difference is incredibly small, far too tiny for any human senses to detect, but it is powerful evidence that the solar system is part of a vast, layered hierarchy of motion. So how fast are we moving relative to this ancient glow? The answer is astonishing, hundreds of kilometers every second. That is the speed at which we are plunging through the universe's background light, like a spaceship that never slows down, with no intention of stopping. And the key insight here is that this motion is not caused by the sun alone, nor the Milky Way alone, but by even larger gravitational structures. clusters of galaxies tugging at us, superclusters pulling us along, and the fabric of space expanding beneath everything we know. This motion means that, in a cosmic sense, there is no such thing as standing still. Even if you could turn off Earth's spin, freeze the sun's orbit, and pause the galaxy's rotation, you would still be drifting through the universe like a lone fleck of dust carried by a cosmic breeze that never stops blowing. The cosmic microwave background is our ultimate frame of reference, the closest thing the universe has to a stationary backdrop. Everything, every star, galaxy, nebula, and particle is in motion relative to it. When scientists measure our velocity through this background, they are effectively measuring how fast we are moving relative to the universe itself. And that motion is not random. It tells a story. It reveals that our galaxy is part of an enormous flow shaped by gravitational forces on scales far larger than the Milky Way. We are moving because nearby galaxies pull on us. We are moving because galaxy clusters exert their gravity from afar. We are moving because the entire region of space we inhabit is being drawn toward even grander structures. The cosmic microwave background does not just illuminate our speed. It maps our place in an interconnected cosmic dance stretching across billions of light years. The surprising thing is how smooth this motion feels from our vantage point. Earth is going about its business, turning, orbiting, circling, spiraling, while the entire solar system glides through this ancient radiation without so much as a cosmic breeze brushing our hair. The background light is not something we swim through or collide with. It is simply everywhere, a uniform sea of photons that gently reveals our motion only to those who know how to look. Yet the philosophical impact is tremendous. It means that the solar system is not simply a participant in the Milky Way's dynamics. We are passengers inside a galaxy that itself is a passenger inside an even larger gravitational structure. And all of this is drifting through the diluted afterglow of the Big Bang. It is a layered motion, like riding a train that is on a ship, that is floating down a river, that is flowing across a continent, that is drifting atop Earth's mantle. Every level adds another vector to the journey. Relative to the cosmic microwave background, we are not grounded. We are not anchored. We are drifting through the universe's first light in a direction that keeps changing as the sun orbits the galactic center, and the galaxy itself flows through the cosmic web of gravitational connections. In many ways, this ancient radiation serves as the universe's quiet reminder that everything is in motion, even the things we imagine as fixed. To drift through the oldest light in existence is to participate in the universe's longest story, a journey that began before galaxies formed, before stars ignited, before anything recognizable existed. Earth is not just orbiting a star. Earth is gliding through the echo of the beginning, carried along by motions so vast that human language strains to describe them. And every second, without fanfare, we slide a little farther across the dim afterglow of creation. If you thought the sun's journey around the Milky Way was impressive, zoom the camera out a little more and things get downright operatic. The Milky Way is not gliding alone through space like a solitary cosmic ship. It is part of a small neighborhood of galaxies, charmingly named the Local Group, that interacts through gravity in a slow-motion ballet spanning billions of years. And at the heart of this dance is the Milky Way's long, inevitable drift toward the Andromeda galaxy, our nearest large neighbor, and the future scene of one of the most majestic collisions in the universe. Earth, clinging to the Sun as always, is along for this entire intergalactic waltz. The Local Group is not a bustling galactic metropolis. It is more like a quiet cosmic cul-de-sac containing a handful of major galaxies and dozens of dwarf companions sprinkled around them like decorative pebbles. The two giants are the Milky Way and Andromeda, each spiraling gracefully through space with their own retinues of stars, planets, and mysterious dark halos. A third sizable member, the Triangulum Galaxy, hovers nearby like a curious neighbor watching the slow approach of two titans. Together, these galaxies are bound by gravity, drifting collectively through the cosmic landscape, even as they subtly tug on each other across millions of light years. The Milky Way and Andromeda are the main characters in this long story. For billions of years, they have been inching closer, though inching in galactic terms means hundreds of kilometers per second. If you could look at the two galaxies from a cosmic balcony seat, you would see them approaching along an invisible gravitational slope, not because one is chasing the other, but because both are falling toward each other. It is less a cosmic duel and more a slow, mutual tumble, two enormous spirals spiraling inward, pulled by the gravitational attraction of their combined mass. The thought of galaxies colliding might conjure images of stars smashing together like cosmic billiard balls. But space is vast enough that most stars will never physically collide. Instead, the collision will reshape orbits, stretch spiral arms, and throw star systems into new trajectories like dancers changing partners in a bustling ballroom. The real drama plays out in gravitational fields, not fiery impacts. But that drama is still enormous, and Earth's path is one small thread in this enormous gravitational tapestry. Even now, long before the grand finale, the Milky Way is already responding to Andromeda's pull. The entire galaxy drifts toward its neighbor with a motion so slow relative to human lifetimes that it might as well be paused, but so fast relative to cosmic scales that nothing can stop it. This motion adds a gentle vector to Earth's path, an additional layer of drift atop all the others. Earth orbits the Sun. The Sun circles the Milky Way, and the Milky Way itself is inching closer to Andromeda in a cosmic courtship that will not culminate for billions of years. If you imagine Earth's motion as a series of nested flows, planet around star, star around galaxy, this intergalactic motion becomes the next great river we drift along. It is the wide, slow current beneath all the smaller ones. Though we do not feel it directly, this motion anchors us inside a much larger gravitational structure. The Local Group is like a loosely bound family of galaxies, each one moving according to the pull of the others, each one shaping the trajectories of its neighbors, even across unfathomable distances. Andromeda itself is not approaching perfectly straight on. It has its own sideways drift, a slight lateral motion that sets the stage for a much more intricate collision than a simple head-on crash. When the two galaxies finally meet, their motions will weave together in a complex gravitational dance. Tidal tails will form, spiral arms will twist and stretch, and colossal streams of stars will be flung into new regions of intergalactic space. In all this, the Sun, if it still exists by then, may find itself in a dramatically rearranged galaxy, perhaps flung to a new orbit, or cast out into a tidal stream wandering between the merged galaxies. But that finale is unimaginably far away. For now, what matters is that the Milky Way's motion toward Andromeda is a real and present part of Earth's larger journey. Even though this motion is not something we perceive directly, it subtly warps the path our galaxy takes through the cosmic web. It also shapes the gravitational environment around the Milky Way, influencing how the galaxy tilts, shifts, and responds to other members of the local group. This motion reveals something profound. Earth is not merely traveling around the Sun or drifting through the Milky Way. It is participating in a grand intergalactic migration. Every second of every day, the entire solar system is creeping closer to another galaxy, one that glows fiercely in the night sky, even though it is still over 2 million light years away. It is the cosmic equivalent of watching a distant mountain on the horizon and knowing, absolutely knowing, that one day you will stand right where it now looms. In this vast gravitational dance, Earth is a passenger who cannot see the choreographers, but who follows every step with unwavering loyalty. Our motion is not defined by a single orbit or a single force, but by layers of gravitational influence from scales both small and cosmic. The local group is our stage, Andromeda our approaching partner, and the Milky Way our current home in a dance that will continue long after Earth's mountains have eroded and its oceans have vanished. And through it all, we drift, quietly, inevitably, toward a meeting written into the universe's deepest gravitational script. If you have ever walked through a crowded room and suddenly felt yourself drifting toward a cluster of people without quite knowing why, you already understand something about the universe on its grandest scales. Galaxies behave in a surprisingly similar way. They gather, cluster, drift, and converge toward regions where gravity whispers the loudest. And our own Milky Way is not choosing its direction freely. It is being pulled steadily, silently, toward a gravitational anomaly so massive and so strange that astronomers named it the Great Attractor, which sounds like either a cosmic phenomenon or a magician who insists on dramatic capes. To grasp this colossal influence, you first need to picture the neighborhood we actually live in, not the local group, but something far larger. Our galaxy belongs to a titanic continental scale structure known as the Laniakea supercluster. This is not a neat, bounded island of galaxies, but a vast, sprawling region in which tens of thousands of galaxies flow along gravitational pathways, like raindrops sliding down the same complex of hills. Laniakea is so large that even the word enormous tries to slip out the back door in embarrassment. It stretches across hundreds of millions of light years, an interwoven cosmic watershed where gravity shapes the motion of entire galaxy clusters. Within this gravitational landscape lies a particularly powerful region, the Great Attractor. The name emerged before astronomers had any idea what it actually was, just that galaxies in our vicinity seem to be moving toward a specific patch of sky in a way that could not be explained by their local interactions. The Great Attractor was like a gravitational rumor, clearly influential, definitely real, but hidden behind a curtain of dust and stars from our vantage point in the Milky Way. At first, astronomers were not sure whether it was a single massive object, a cluster of galaxies, or cosmic tax collection day for everything in the neighborhood. Eventually, as observational tools improved, we discovered that the Great Attractor is more of a gravitational focal point than a single structure, part of an even larger concentration of mass called the Norma supercluster. Imagine a valley in a mountain range where rivers naturally converge. The Great Attractor is one such valley, and galaxies like the Milky Way are the rivers. We are streaming toward it, not because it commands us directly, but because the entire gravitational terrain of Laniakea slopes gently downward in its direction. This slope is not something we feel. It is not a cosmic wind or a force that pulls at your stomach the way an elevator does. Instead, it appears in the peculiar velocities of galaxies, the subtle deviations from the motion caused by the expansion of the universe. Space itself expands in all directions, but galaxies within Laniakea do not simply drift apart with this expansion. Many of them have an additional motion superimposed on top of it, sliding toward the Great Attractor, like marbles settling at the bottom of a vast bowl. The Milky Way is no exception. Our entire galaxy, with its hundreds of billions of stars, its swirling arms, and its secretive dark matter halo, is drifting toward this gravitational low point at hundreds of kilometers per second. It is as though the universe has placed us on a moving walkway without telling us the destination. Earth, orbiting the sun in blissful unawareness, is participating in this massive migration. We are not just circling a star, not just orbiting a galactic center, not just approaching Andromeda. We are gliding along a gravitational current carved by structures so vast that their edges may never be fully known. The most astonishing part is that the Great Attractor is only one influence among many. Beyond it lies another even more massive region called the Shapley concentration, a gigantic cluster of clusters so dense with galaxies that it bends the paths of everything in its vicinity. Some researchers believe the Great Attractor is merely the local foothill on a slope leading ultimately toward Shapley, meaning we are traveling not toward a single gravitational destination, but along a ridge connecting multiple colossal structures. It is the cosmic equivalent of discovering the hill you thought you were climbing is part of a mountain range stretching beyond the horizon. This layered motion reveals something profound about our place in the universe. Earth's journey is not just planetary, not just stellar, not just galactic. It is supercluster scale. Our path is shaped by tides of gravity flowing across distances so great that light needs hundreds of millions of years to cross them. We inhabit a universe where motion is inherited from motion, where every orbit is embedded inside a larger drift, and where even the largest galaxies are mere specks carried along by the gravitational terrain sculpted at the birth of cosmic structure. And yet, for all its immensity, this motion has no effect on our daily lives. Birds still migrate, oceans still swirl, and your coffee still tastes like coffee instead of existential dread. But in the quiet background of everything you do, Earth is part of a galaxy softly pulled toward a mysterious region we cannot see with our own eyes. The Great Attractor does not roar, it does not glow, it does not announce itself, but its influence is written into the very motion of the Milky Way. So Earth drifts, not just through sunlight, not just through starlight, but through a gravitational landscape whose contours span the largest structures in the universe. We are passengers in a cosmic migration far beyond the scale of galaxies, following paths carved by mass accumulations so immense they defy easy comprehension. Our destination is not a point, but a journey, one guided by the invisible scaffolding of gravity that threads through all of space, drawing us steadily forward into the vastness of Laniakea. If you imagine space as a perfect vacuum, a serene nothingness so clean you could drop a white sock and never worry about it getting dirty, you're in good company. Most of us grow up with that picture, planets drifting in a silent, empty void where nothing stirs unless a comet decides to make a dramatic entrance. But the truth is far messier. Space is not empty. It is filled with an enormous, sprawling, ever-changing ocean of dust grains, charged particles, wisps of gas, relic atoms from ancient explosions, and mysterious filaments of interstellar material that wander like ghosts through the galaxy. And our solar system does not simply sit in this ocean. It plows through it non-stop, carving a long wake as it moves. Picture the sun as the prow of a ship sailing through a restless sea. The solar system is not gliding gently across calm water. It is pushing against streams of material that drift between stars. Some regions are thin and diffuse. Others are denser and textured, but none are truly empty. Every handful of millions of kilometers brings a slightly different environment, a new pattern of particles, a fresh mix of interstellar dust and gas. The galaxy is full of currents and tides, and we sail through them as naturally as fish swim through the ocean. This material is mostly harmless on the scale of minutes, hours, or even centuries. Earth does not wake up one morning covered in cosmic soot, nor does the atmosphere sneeze because a new cloud of interstellar hydrogen floated by. But over millions of years, these slow interactions accumulate effects, small influences that quietly nudge the environment we live in. Earth's long-term climate, the shape of the heliosphere, the flow of cosmic radiation, and the distribution of charged particles drifting near our atmosphere are all affected by the invisible weather of interstellar space. Dust is one of the most surprising components. These are not the dust bunnies hiding behind your bookshelf. They are ancient particles forged in the atmospheres of dying stars, cracked apart in supernova blasts, and swept across the galaxy like microscopic travelers with nowhere specific to go. When the solar system encounters regions rich in this dust, the sun's protective bubble, the heliosphere, can be nudged or squeezed as the solar wind fights to push the dust-laden plasma outward. A denser interstellar region acts like thicker water against a ship's hull. The sun must work harder to maintain the size of the bubble that shields Earth from cosmic rays. Then there are streams of charged particles, cosmic rays that zip through space at nearly the speed of light, born from supernova shock waves, stellar flares, and energetic processes that have been happening since long before the sun existed. The heliosphere usually deflects many of these particles, but its strength is not constant. When the solar system enters regions of space with different densities or magnetic fields, the heliosphere can expand or contract, changing how many cosmic rays reach Earth. These shifts have been subtle participants in the planet's climate history, influencing the formation of atmospheric ions and possibly playing faint roles in cloud formation over geological time. Interstellar gas also contributes to this quiet cosmic weather. Hydrogen and helium atoms drift through the galaxy in diffuse clouds, and the solar system's motion means we regularly encounter variations in their density. These atoms can slip across the boundaries of the solar wind, mingle with charged particles, and influence the shape of the heliosphere's outer boundary. Nothing catastrophic happens. Earth isn't swallowed by a gas cloud or smothered by interstellar haze, but the long-term patterns of solar radiation and cosmic ray shielding experience small but real changes. These environmental shifts happen on timescales so long, they make the age of the pyramids feel like a weekend getaway. But geological layers, ancient climate proxies, and the behavior of long-term cosmic radiation markers hint that Earth may have experienced subtle environmental variations corresponding to the solar system's passage through different interstellar regions. These are not dramatic moments, no sudden cosmic storms or apocalyptic blizzards. Instead, they are gentle changes in the background conditions, like slight tides changing the coastline over millennia. Our intuitive view of space as an endless vacuum hides the real complexity of this journey. Between the stars lies an enormous mixture of matter that never rests. Clouds of gas stretch for light years. Streams of dust drift in elongated trails. Filaments of plasma twist within the galaxy's magnetic fields. The solar system encounters these regions slowly, steadily, without fanfare. But each encounter leaves fingerprints on the cosmic environment Earth depends on. Even the solar wind, the stream of charged particles flowing outward from the sun, is shaped by what it meets. As the solar system enters different interstellar zones, the wind compresses, expands, or shifts its magnetic configuration. Earth lives inside this bubble of solar influence, meaning the sun's interaction with interstellar material becomes our interaction too. We are not isolated from the galaxy. We are immersed in it, bathed in ancient particles, drifting through cosmic weather that never turns off. So the next time someone imagines space is empty, you can think of the solar system pushing through a mist so thin you could fly through it without noticing, yet so persistent that it shapes the sun's protective bubble and influences Earth's environment over eons. We are not traveling through nothingness. We are traveling through a galaxy that breathes, flows, and drifts with material older than Earth itself. Space is not empty. It is simply patient, and we are endlessly passing through it. When you rewind Earth's history far enough, past the rise and fall of continents, past the birth of oceans, past the earliest creatures crawling out of the water, you eventually collide with a strange truth. Our planet's story is not just written by geology and biology. It is also written by the galaxy itself. The path Earth takes through the Milky Way is not merely a backdrop to life. It is an active participant, quietly influencing long-term climate trends, altering the cosmic radiation that reaches the surface, and perhaps even nudging the timing of mass extinctions. If Earth had a very old scrapbook hidden somewhere in its mantle, you would probably find cosmic fingerprints all over the pages. To understand why, imagine Earth drifting through an ever-changing cosmic environment for billions of years. Every few 100 million years, we complete a lap around the galactic center, but that lap is anything but serene. Along the way, we pass through denser regions of interstellar matter, encounter clusters of energetic stars, approach lingering remnants of supernovae, and sometimes slip between quieter stretches where cosmic rays decrease and radiation levels ease. These transitions unfold slower than continents drift, slower than mountain ranges rise, but over millions of years they add up, subtle environmental pressures layered onto the biology and climate of Earth like faint whispers from the galaxy. One of the biggest questions scientists have wrestled with is whether our galactic journey influences mass extinctions. The fossil record shows that Earth has experienced numerous catastrophic die-offs, some spectacular, some quiet, some bewilderingly abrupt. While many have obvious causes, such as volcanic outbursts or asteroid impacts, others carry a faint cosmic aroma, as though the universe may have had a hand in rearranging life's timeline. One hypothesis suggests that when the solar system drifts into regions dense with nearby massive stars, those cosmic overachievers that burn hot and die young, the chance of exposure to higher radiation increases. A nearby supernova, even at a safe cosmic distance, could bombard Earth with energetic particles capable of disturbing atmospheric chemistry, stripping ozone, or subtly stressing ecosystems. These events are not the everyday kind. They are exceedingly rare in human terms. But across hundreds of millions of years, Earth has likely experienced several episodes of heightened cosmic radiation. Geological markers, such as unusual isotope ratios, hint that our planet may have been brushed by the effects of distant stellar explosions, leaving faint scars in sediment layers like footprints from a passing giant who never meant to step too close. Then there are long-term climate cycles, mysterious fluctuations that play out over tens of millions of years, too slow and broad to be explained by plate tectonics alone. Some researchers propose that these cycles may correlate with Earth's oscillations through different regions of the galaxy. As the solar system meanders between denser and thinner patches of cosmic material, the heliosphere, the sun's protective bubble, expands and contracts. When it contracts, more cosmic rays may reach Earth's atmosphere. Cosmic rays are not just high-energy party crashers. They may influence cloud formation, subtly shifting global temperatures. Over deep time, even a slight nudge in atmospheric patterns could contribute to broad climatic transitions, cooling periods, warming phases, or shifts in the distribution of ice. Even the sun's vertical oscillation through the galactic disk plays a role here. When the solar system dips into regions where stars are more densely packed, Earth becomes more exposed to stray cosmic influences. When we rise into quieter territory, cosmic radiation eases and the environment steadies. Nothing about these transitions is sharp or sudden. They unfold like chapters in a slow-motion documentary. But the Earth we know, its climates, its oceans, its biological diversity, has been shaped partly by these cosmic cycles. There is also the intriguing possibility that passing near giant molecular clouds could have affected Earth's past. These clouds contain thick swaths of gas and dust. If the solar system ventured close enough to one, it might compress the heliosphere significantly, allowing more cosmic radiation to seep in. In extreme cases, such a cloud could even block sunlight, chilling the planet for thousands of years. While evidence for these events remains subtle and debated, their potential influence adds another layer of cosmic complexity to Earth's deep-time climate story. Even asteroid impacts may not be entirely divorced from our galactic migration. As the solar system drifts through different gravitational environments, distant reservoirs of comets, especially the outermost cloud enveloping our planetary neighborhood, may experience tiny perturbations. Over immense timescales, such perturbations could knock icy visitors inward, increasing the likelihood of collisions. It's not that the galaxy is hurling rocks at us intentionally, but rather that gravitational ripples accumulate like small waves, nudging driftwood toward the shore. What emerges from all of this is a picture of Earth as a world whose history is braided tightly with the galaxy. Life on this planet has adapted not only to shifting tectonic plates, erupting volcanoes, and wandering climates, but also to the faint but persistent influence of cosmic neighborhoods. We are children of the Milky Way as much as we are children of Earth. Yet it's important to remember that the galaxy doesn't micromanage. It does not plan extinctions or sculpt species with a deliberate hand. Instead, it provides the broad environmental canvas on which Earth's story unfolds. Cosmic radiation waxes and wanes. Interstellar conditions shift. The solar system's shield expands and contracts. These are not commands, but gentle environmental pressures, occasional nudges that shape the backdrop against which evolution works its magic. When you zoom out far enough, you begin to see Earth's deep past as more than a geological timeline. It becomes a cosmic timeline, written partly in starlight and interstellar dust, mass extinctions, climate cycles, evolutionary bursts, all lie atop a galaxy that has been whispering into Earth's environment for billions of years. And through it all, the planet simply keeps traveling, spinning through an ever-changing galactic landscape that will continue shaping its future long after humanity has become just another footnote in the cosmic scrapbook. Projecting Earth's future across the next billion years requires a kind of imagination that blends astronomy with patience, because nothing about the cosmos unfolds at a human pace. Stars shift like slow dancers, galaxies drift like enormous lanterns on a cosmic tide, and entire civilizations could rise and fall before our planet even completes a fraction of its galactic loop. Yet Earth is moving, always moving, and that motion guarantees one thing: the future will not be static. The galaxy will continue sculpting the environment around us, just as it has done quietly for billions of years. Picture Earth 1 billion years from today, not as a futuristic metropolis or a scorched wasteland, but as a traveler still faithfully orbiting the sun, still drifting along that spiraling, bobbing, twisting galactic path. By then, the continents will have rearranged themselves into new supercontinents. The oceans will have shifted like slow blue ink, and the sky will have a different cast of nearby stars. The sun will also have grown subtly brighter, nudging Earth's climate toward warmth in slow degrees that would make today's weather reports look like scribbles on a napkin compared to a Renaissance fresco. As Earth continues its long ride around the Milky Way, it will wander through new cosmic neighborhoods that may gently shape the conditions for whatever life still exists. Perhaps we will drift into regions where interstellar material thickens, altering the boundaries of the sun's protective bubble. Maybe we will pass through zones where cosmic radiation ever so slightly increases, adding faint pressure on whatever ecosystems thrive at the time. These changes won't appear as sudden shocks. They will be cosmic nudges, long-term influences unfolding so slowly that only the rocks and oceans will notice. By the time another 250 million years pass, Earth will have completed one full orbit of the galaxy, returning roughly to where it started. Though returning is a generous word for a galaxy that constantly evolves, churns, and shuffles its stars like a deck of cards. Nothing will look the same. Constellations we cherish today will be distorted beyond recognition. Familiar celestial landmarks may have drifted or vanished entirely. New stars may blaze near the sun, while others fade or move away. Earth's night sky will be a new story painted on the same ancient canvas. Fast forward even further, and the approach of the Andromeda galaxy begins to matter. Not in an apocalyptic sense. Earth will not explode or be flung across the universe like a misplaced frisbee, but in a grand architectural sense. As the Milky Way slowly bends toward Andromeda, the sky will begin to show hints of the approaching spiral, growing from a faint smear to a magnificent celestial bloom, visible even in broad daylight. If any life still exists on Earth, whether microbes clinging to hydrothermal vents or some distant descendants of humanity, They will witness a slow-motion galactic embrace that reshapes the heavens with astonishing beauty. The eventual merging of the two galaxies will take hundreds of millions of years, long past the point when species come and go, climates transform, and the sun gradually brightens toward the end of its comfortable, steady phase life. Earth's orbit may shift slightly during this intergalactic romance, perhaps settling into a new position within the merged galaxy's gravitational structure. If the sun survives the tumult, likely sailing through relatively untouched, Earth may continue its long drift through a remade galactic landscape. The sky will glow with new patterns of stars pulled into flowing arcs, tidal streams, and colossal currents of light. For life still clinging to the planet, it would be as if the universe decided to remodel the ceiling without asking permission. But far sooner than that, the sun will begin its slow transition into a more temperamental, brighter star. Hundreds of millions of years before it becomes a red giant, the sun's growing heat may cause oceans to shrink and climates to tighten. Earth's biosphere will adapt as long as it can, shifting and reshaping in response to the planet's changing conditions. Life has proven astonishingly resilient across deep time, so it may persist in ways we cannot imagine. It may retreat underground, migrate to cooler pockets, or evolve into forms that thrive in new environmental niches shaped by both solar evolution and cosmic drift. And yet, for all the grand arcs and dramatic cosmic movements, Earth's role remains deeply humble. It is a hitchhiking world, clinging to a star that's clinging to a galaxy that's clinging to a supercluster that's drifting through the deep gravitational fabric of the universe. Earth is not charting its own course. It is being carried gently, inexorably, through environments it does not control, through cosmic weather it cannot negotiate, through a universe that operates on scales so vast that even imagination feels taxed. But perhaps that is the wonder of it. The universe is not static, not frozen, not sitting politely in a cosmic display case waiting for us to visit. It is moving, every atom, every star, every planet. Earth's future is one chapter in a story written in motion, a story where the galaxy rearranges itself. The universe expands into deeper quiet, and the sun ferries its tiny blue companion through regions of space that have never known life until Earth passed through. If Earth could speak, it might look around the universe and say, "I don't know where we're going, but I trust the ride." And maybe that is the most cosmic truth of all. We are passengers in a universe that never stops traveling, riding a star that never stops moving, on a journey with no fixed destination, only motion, change, and wonder stretching endlessly ahead.